It will be mostly focused onto the bearing systems which we use mostly for bridges, but also nowadays the technology has so evolved that the bearings are not only being used in bridges, but they are also used in other structures like buildings, etc. And therefore, we are no longer calling them as bridge bearings. We are calling them as structural bearings. So in today's discussion, we will be starting with the basics, of course, that what exactly is a structural bearing by its definition and where it is used, what are its applications. Then we will be going through the different options of bearing systems, what are their individual advantages and limitations. We will be discussing in little detail what is the state of the art technique or the bearing systems being used in our country and what are the further innovations and advancements there. And there towards the end of the presentation, we will be touching briefly, of course, the aspects related to the performance like design, manufacturing and installation, and we will conclude the discussion with a few project references or case studies. So to start with the discussion on the product, that is structural bearings, and as the definition goes, the bearing we say that it is a mechanical device which is installed or provided in between the substructure part, that is the pier and the pedestal, and the superstructure part, which is the deck segment over which we have our vehicles going. And this device is provided in between these two parts to control their interaction. The function of a bearing is to not only safely bear and transmit the loads and forces from the superstructure to the substructure, but also at the same time to allow adequate degree of freedom in terms of translation and rotation that is required by the superstructure, because we all know whether the structure is made up of concrete or steel, it has the influence of temperature, and under the temperature influence it has thermal expansion and contraction. So it requires certain freedom to move, and not only by this thermal expansion and contraction, by the influence of the live loads or the wind and seismic, there may be certain additional movements and rotations in the structure, and the bearing system has to complement all these functions of the structure. So this mechanical device is the bearing, and this is the function of the bearing. When we talk in terms of bridges, bearings comes under the terminology called bridge appurtenances. And along with the bearings and the bridge appurtenances, we also count expansion joints. If you are able to see my pointer on the screen, I am trying to point out where exactly these devices are installed. Let's say this is a typical bridge, and we have 4 spans in this structure, and these are the piers, intermediate piers, and we have 2 abutments. So the expansion joint is installed at the deck level. It may be at the junction of the deck and the road surface at the abutment, or depending on the design of the structure, it could be also on certain intermediate pier locations. Next to the expansion joints, we have the bearings, which will be the topic of discussion for today. And the bearings, as I already explained, they are mostly by and large installed at the support in between the piers on the deck or at the abutment location in between the deck and the RE walls. Sometimes in some special application, special bridges, the bearings are also installed under the articulation span. That means there will be a projection from one end of the deck which is supporting the bearing, and the other end of the deck will be resting on top of it. So those are certain special applications, we will discuss them later. And besides the joint and the bearing, sometimes in some special cases the bridge has some other appurtenances also, which are the shock transmission units or the seismic devices. So basically, this is where the bridge bearings are applied into a bridge structure. Now talking about their types, the types are many, and they all have their own application areas. We start with the steel bearings first in discussion, which includes the steel rocker and roller bearings, hinge and plate bearings. We can also say that these are the very first or the initial type of bearings which are used in the bridge structures or which were used. Then came in the elastomeric bearings. These are rubber based products. Then we will also briefly go through the disc bearings in the discussion. We will also see pot and pot cum Ptfe bearings, which are quite popular bearings in our country also. Along with pot and pot Ptfe bearings are fixed and metallic guide bearings, which are always or often used in combination with pot bearings for situations where heavy horizontal force is there. Then we will talk in little detail about the spherical bearings because these are the state of the art and most latest technology and being widely used in our country these days. And talking about the further evolutions, we will also discuss in brief the sliding isolation pendulum bearings. So now going about these bearings one by one, first talk about the conventional bearing systems, which are mostly the steel bearings. On your left side in the screen, you see rocker and roller bearings. As you can see by yourself and also in the photograph of a real bearing system, these bearings are all made up of completely steel components. And the interface of the sliding components also is steel to steel. So the main issue with these bearings is if there is too much of movement or rotation taking place in the bridge, because two hard surfaces are sliding against each other, so there is a lot of abrasion and wearing of the components is taking place. And vice versa, if the structure is not really moving and the components are in the dormant state for a long period of time, then two similar metals, if they are kept in open environment for a longer period of time without disturbing their state, then the ions interchange and then a fusion takes place. So all this leads to the repetitive wear and the frequency of repair and replacement for these bearings is very high. In addition to this, whenever we talk about the bridge bearings, we have to understand that we always talk about how many degrees of freedom that we need to provide in our structure. At max, talking from the bearing point of view, there may be 6 degrees of freedom. And these 6 degrees of freedom, if we go into a breakup, 3 are associated with movements in 3 directions, longitudinal, transverse and vertical. And the other 3 degrees of freedom are associated with rotations about these 3 axes. So depending on the type of application and the design of the structure, a bearing system may require anything between from 2 degrees of freedom to up to 5 degrees of freedom. So if we talk about the conventional steel bearings, and you can just look at this image, because of the continuous long roller length, the problem with this bearing is it can offer movement in the longitudinal direction. It can also offer rotation about transverse axis of the bearing. That means if the girder due to live load is sagging, it can take that rotation. But these bearings, they cannot offer any rotation in the transverse direction because there is a long roller which prohibits the bearing to tilt laterally. So there the degree of freedom is restricted. And sometimes due to concentration of loads, the rollers, because they have a point load contact, they give away, and therefore this adds to another demerit of this bearing system. So these were one of the very preliminary and you can say the start of the bearing systems worldwide. And these are the very basic bearings used in our structures decades ago. Then the technology of the bearing systems advanced and came into practice the elastomeric bearings. In India, we have IRC 83 different parts, which are the codes and guidelines for the use of bridge bearings. IRC 83. Sorry.
Very lives in Bangalore.
Acha, you are based in Bangalore.
No, I'm based in Delhi, but my family lives in Bangalore.
Bangalore.
Okay. So elastomeric bearings came into practice in India in 1980s, early 80s. There was the first code on elastomeric bearing published in 1982. As the name itself implies, elastomeric bearings consist of rubber mainly, And you can see in this image, it's a bearing which is black in color. That is how the neoprene compound looks like after vulcanization. And this bearing has internal steel laminates, which provides this bearing the load bearing ability. So by virtue of the elastomeric component, the bearing is flexible enough to accommodate structural movements and rotation. It offers good damping characteristics as well. The translations and rotations both are offered by virtue of the elastomer deformation or deflection. So this way the bearing takes care of the movement and rotation by self-deformation. But this again is a sort of limitation also, because if we try to use these bearings in very long spans, let's say spans more than 25 or 30 meters, then because the structure is requiring a larger magnitude of movement and rotation, and the bearing has to have a lateral deformation in higher values, over the period of time that may lead to certain wear and tear in the bearing system. So in general, it is said that the elastomeric bearings are suitable for small to moderate spans. However, nowadays there are improved compounds available and the technology of manufacturing has also improved. So the bearings are being used nowadays for large span structures also, but those are exceptional cases. So we can say for general understanding that the elastomeric bearings are safe and good for use in small to moderate span values. To understand in little detail about the geometry of the elastomeric bearings, how it looks like from inside, we have this exploded view of the bearing. We have the bottom layer of elastomer. Then we have a layer of steel sheet, and subsequent layers of elastomer and steel makes the total height of the bearing. So the internal steel laminate reinforcement provides this bearing ability to withstand vertical loads and horizontal forces, whereas the elastomer component provides us flexibility for lateral deformation to take movement and rotation. So this one was a standard elastomeric bearing which takes care of free movement and rotation in all directions. This is how the bearing takes the rotation by eccentric compression. Then if the force requirement is higher, there are possibilities, and this is covered in the code, that the standard elastomeric bearings can be clubbed or combined with additional steel plates on top and bottom, so that the movement of the bearing can be restricted or checked in any particular direction or maybe in both directions, and then this bearing becomes a fixed elastomeric bearing. The earlier one was having the restriction only in one side, and this bearing has the locking plates on both sides, longitudinal transfers. So this bearing only takes care of the rotation, but it is not free to provide any movement in any direction. Next in the category is the disc bearings. Disc bearings, I can tell you that these bearing systems originated in US, and they started using these bearings around 1960s and 70s, and these bearings can be considered as a hybrid bearing system, having a combination of the benefits of elastomeric element, which is a polyether urethane disc, along with the steel components. And the good thing about these bearings is, in addition to satisfying the rotation requirements, they were able to transfer very heavy horizontal forces, which was a limitation with the elastomeric bearings. Uh, these are low profile bearings because the elastomer is very thin, and it is the shear restriction mechanism is confined within the thickness of the elastomer. So the overall height footprint of the bearing is very small, and the polyether urethane element has very excellent long-term and aging properties, and therefore the durability of these bearing systems is better as compared to a elastomeric bearing. But the limitation they have on the other hand is the high stiffness of this polyether urethane disc, and because of its very high stiffness, the restoring moment getting generated in these bearings is very high, which could be a cause of concern for the structure and as well as the sliding surface which is mounted on top. And also these bearings has comparatively lesser rotation capacity as compared to pot and spherical bearings. The concept also started in US. They are still using these bearings, but if we go to the European markets or the European code and specifications, they for some reason do not have a code on disc bearings. They decided not to include disc bearings in their possible choices. So for that reason, the disc bearings are finding their applications in mostly American bridges, but they are also not that popular in Europe as well as in India. Next, in the types of the bearings are the pot Ptfe, and I must say these have been the most widely used bearings in our country. The code on these bearings, IRC 83 Part 3, it came into practice first in the year 2002, and now I think in the year 2018 we have a full-scale revision of this code, and we have changed it to the limit state concept of design. The concept of pot Ptfe bearing is very simple. It works on a similar concept on which a hydraulic assembly works. Normally, if you have seen a hydraulic jack or something, it has a cylinder, steel cylinder, and which has fluid inside, and there is a piston on top. So the similar arrangement is there in pot Ptfe bearings. I try to explain you by this video. There you see it has a cylinder and a disc of elastomer inside. Let me just go back a few slides. Yeah. So we have this steel cylinder at the bottom and the disc of elastomer which sits inside the cylinder. And there are some sealing rings which locks this elastomer disc inside the steel cylinder, and it is covered on top by another steel component called piston. So in this assembly, once the elastomer is sealed inside the two steel components, it acts as a fluid under pressure. And when the bearing is provided with some eccentric loading or it is to take a rotation, the elastomer very easily tilts and it offers that rotation. That was a fixed type. And when the bearing is required to take movement, the piston design or shape is changed and it is provided with a sliding material on top, normally Ptfe. And a third additional component is introduced, which is a flat sliding plate on top. And this slide plate is provided with a thin sheet of stainless steel underneath. So in addition to satisfying the rotation, which is by virtue of the elastomer disc, this particular bearing is also able to provide free movement or translation in both longitudinal and transverse directions. So the bearing takes the movement and the bearing also takes the rotation because the elastomer disc is there inside. And the third configuration of a pot bearing is the guided bearing, which has some guides or locking keys which restricts the movement of the bearing in one direction, and the bearing is then only free to move in other direction. So the configuration, or you can say the combination of these three types, whether it is elastomeric bearing, it is pot, or it is any other bearing, a combination of fixed bearing, which is taking only the load and forces and rotation, free bearing, which is providing bidirectional movement, and guided bearing, which is providing unidirectional movement. The combination of these three bearings is provided in any bridge and they satisfy the structural requirements together. Talking about the pros and cons of pot bearings, first discussing about the advantages. In case of pot bearings, the limitations of other forms like steel bearings, elastomeric and disc that doesn't exist. Pot bearings can satisfy up to 4 degrees of freedom. They can be designed with uplift mechanism to take care of the tension forces or anti-uplift forces. And each and every component of the pod bearing is possible to replace easily. So hence these bearings, they come very handy and very easy as far as the maintenance aspect is concerned. On the limitations, the pod bearings, because of the restoring movement, because wherever the elastomer is involved, there is a restoring movement issue involved, and because of that, they have the gapping effect. We will see this in the coming slides. There are too many loose components in the assembly of pod bearings, so it is prone to wear and tear more as compared to other bearing forms. And the elastomer has a spring characteristics which could be a concern for certain structures like continuous bridges or rail bridges. And if it is a service uplift situation, the pod bearings may not be the best suitable choice. We will be discussing these points in little detail in the coming slides. Now coming on to the bearings for modern bridges. So we have discussed so far the conventional bearings, then changing to elastomeric, disc also we have understood, and pod bearings. Now what are the bearings for modern bridges and why at all they are required? So they are required because if we talk about the modern bridges, the requirement has increased a lot, or you can say the demand from a bearing system has increased a lot. Why is it so? Because the live loads have increased. The relation between the dead load and live load is more pronounced. Let us take an example of a railway bridge where the structure itself, the dead load of the structure is not that high because it is a steel structure. But the load of the live load, which is the train moving onto the bridge, is very heavy. So under the influence of this heavy live load, the deflection and displacements will be much bigger as compared to a normal highway bridge, where the structure is very heavy being concrete structure and the live load is comparative to that dead load is not that big. This concerns not only the rotation of the end girder, but it also results in a lot of accumulated movements over the period of time. Also because of the increased axle loads and the moving velocity and speed of the traffic on the structures, the tractive efforts, or you can say the acceleration and braking forces also increased a lot, which is going nowhere else, but the bearing only has to bear and transmit these increased loads and forces. So all in all, we can say that in the modern structures, the requirement from a bearing perspective about the displacement and rotations is higher in terms of frequency, magnitude, and velocity. So looking at the limitations of the existing bearing systems and the needs and demands of the modern structures, we need to have a bearing system which should possess both strength and flexibility characteristics. And by saying so, that means the bearing should be able to have very high loads and forces, but yet it should be able to offer very high velocity, high frequency, and high magnitude rotations and movements. And this solution is found in spherical bearings. Why? Because they can accommodate larger rotations. There are no elastomer pads and sealing elements in these bearings, which eliminates the entire concern of the restoring moment, what we have seen in pod. And they can take very high loads and stresses because overall the entire assembly is mainly a steel component assembly. To understand the geometry of a spherical bearing, let us go through this animation. We have a bottom concave component or a spherical component, you can say, from where the name of this bearing is derived, and there is a matching convex component. The translation geometry of this bearing is similar to pod, but the rotation in these bearings is taken care of by curved surface sliding. So this way, these bearings are able to satisfy very large scale rotations also without causing any excessive stress or strain, because even if the rotation magnitude is very small or it is very high, it is only the dynamic friction which is taking place and the value of dynamic friction remains the same. So no matter very high rotation is also required to be satisfied, there is no stress or restoring moment getting developed in these bearings. Having a look at the geometry, this is how a fixed spherical bearing looks like. It is the bottom component which is machined in a concave shape, and there is a low friction sliding material lining which is fixed to this bottom component, and there is a matching convex component on top, and the radius of curvature of these three interfaces are precisely matched. So they together provide the rotation ability. And then there is a top interface of sliding of this low friction sliding material and stainless steel underneath this top ring component, which together makes this bearing system assembly complete. And the bearing is able to transfer the horizontal forces both in longitudinal and transverse direction, and also offers free rotation. This one is a free spherical bearing. So we have the bottom assembly exactly the same. The concave part and the convex part together provides the rotation freedom. And these bearings, they offer the rotation with the minimum resistance because there is no elastomer bed which is to be compressed. So the rotation ability of these bearings is very high with minimum resistance. And this bearing takes care of bidirectional movement. And the last among the basic configuration is a guided one, which is quite similar to a free bearing, only with the introduction of these guides, which runs against two flat parallel faces. So this way the bearing is restricted to move in the lateral direction. It is only free in moving one direction. So up till now, we understood what are the different choices and options of wedge bearings are available at our disposal. And we started from the very old and conventional steel bearings up to the state of the art spherical bearings. And we discussed also what are their advantages and where they are having limitations. Now, going a step further and talking about what are the further improvements or innovations in bearing system, because it is the need of the hour that we keep constantly working on the limitations and the weakest element or weakest part of the bearing assembly. And one of such weakest link or weakest component of a bearing assembly is the sliding material. What is the sliding material? So far, or by and large, the most commonly known sliding material which is being used in the bearing systems is Ptfe. The full form of Ptfe is polytetrafluoroethylene. It is a thermoplastic material. Thermoplastic material means in general we can define it is something in between rubber and steel. It is not as soft as rubber, not as flexible as rubber, but also not as hard as steel. So it is a thermoplastic material, and it offers the lowest value of friction when sliding against the polished stainless steel sheet. So since the bearing has to do a continuous movement in the bridge, and since there cannot be an ideal interface where there is no friction, there will be certain amount of friction. So this friction, what it results? It results in the wear and abrasion of the sliding material. So over the period of time, this sliding material gives away, and the thickness of this material is getting continuously lost. And after a certain magnitude of movement is over, the material might have completely given up. So therefore, it is required that the sliding friction of this interface has to be minimum, so that we can achieve longevity or longer service life and sliding path from the two interface. Ptfe was developed around 1950s, and the application of Ptfe in bridge bearings dates back to around 1960s. Since then, it has done its service pretty well, I must say. But there were certain structures worldwide wherein the demand of these structures was that high that the bearings equipped with Ptfe were not able to deliver a longer service life. As a case study, I have taken the reference of this bridge. It is called Rio Tejo Bridge in Lisbon. You must have seen this photograph or the video of this bridge in many Hollywood movies and all. It is a rail cum road bridge, a suspension rail cum road bridge, and the bearings are installed at the support location. And you can yourself imagine being a steel structure and being a double loaded bridge. It has the rails also therein and road also therein. The dynamic movement of this structure must have been very high. So when the monitoring of the bearing location was done, so with the passage of train in this bridge, high speed train is moving inside, the amplitude of movement at the bearing location is going as high as up to 150 millimeter. You can imagine with every movement cycle of the train inside the bridge is moving backward and forward up to 150 millimeter. That is the magnitude of dynamism in this structure. And when we add up or when we accumulate this high movement over the number of cycles or number of trains passing in a day and the number of days in a year, and when we take the summation, the movement requirement was going up to 10,000 meters a year. You can imagine, it is very difficult to imagine, but a bearing, which whenever we see a bearing, it looks like it is just simply sitting in place. It is not doing any function, but actually it is moving with the bridge. The daily cycle of movement, longitudinal movement, long forward and backward is happening. And when you accumulate such movements in certain structures, it could go up to 10 kilometers a year. So the bridge is stationary at its place, but within the structure, it is moving up to 10 kilometers a year. So this may be funny. It may sound funny, but it is a reality. And the velocity at which this movement was taking place was around 15 to 20 millimeter per second. That means it was moving with a very high velocity. So when this test was done over Ptfe in the laboratory, you could see that after 10 kilometer of slide path with a velocity, very low velocity of 2 millimeter per second, and the normal design stress of Ptfe, you could see the entire Ptfe has given up. It has crystallized and settled in paste form on the mating acid surface. So that means that is the life of Ptfe. That is the limit it can go up to. And with this 10 kilometer in this bridge happening every year, the bearings in this bridge was able to deliver not more than a life of 2 to 3 years in the structure somehow. So that was the time when the need was felt to do the research on a better and improved sliding material. And that was also the time when the German government planned about maglev trains. And maglev trains are magnetic levitation trains. And the parameters for performance which was laid down in the specification for the bridges, that with the passage of every train car, there would be anticipated movement of 7 millimeter at the bearing location, which gives an accumulated total movement in a year of more than 625 meters. That means you can say roughly more than half a kilometer per year. And they demanded a bearing system which should fulfill the service life of 80 years. Now, if we do simple math, if they demand more than half kilometer of movement every year from the bearing sliding surface, and they want the bearing system to last 80 years without maintenance, that means the sliding material must have a sliding capacity of doing more than 50 kilometers. And you see the Ptfe gave up in just 10 kilometers with a very slow velocity. And the velocity at which they wanted the movement to take place was 15 millimeter, about 8 times or 7 times of this velocity. So it was a very high demand. And therefore the research started for this innovative sliding material in Germany. And it started around 1998. And by the year 2002, the material was developed and it got its first type approval for maglev trains by Deutsche Bahn, that is German Railways. And then in 2003, it got its first national type approval, and in 2006, the first European type approval. And by saying European type approval, that means the material has been accepted by the codal bodies to be used openly in bridge bearing applications. So what is this material? Let us first talk about this magic material. What is the name UHMWPE implies for? It stands for ultra high molecular weight polyethylene. In earlier case in Ptfe, it was polytetrafluoroethylene. Here it is ultra high molecular weight polyethylene. So basically, the family is not very different, but the molecular weight of the material in this case is increased very high. The material is modified, the generic material polyethylene is modified with certain special fillers and materials to get the desired properties, and additives were added upon to improve the sliding and load carrying behavior. Since it is also thermoplastic material like Ptfe, it also has the similar properties, but altogether a different level of performance as compared to Ptfe. A similar long-term sliding test was repeated on this material, but with slightly different parameters. In case of Ptfe, it was 10 kilometer. In case of UHMWP, it was tested for 50 kilometer slide path. Velocity was kept up to 15 millimeter per second, and stress level as 60 MPa, which is almost double the Ptfe stress level. And you could see the disc of UHMWP is still intact. You could see very well the dimples, which are there up to half the thickness of the material for holding the grease, which is used for lubricating the surface. And even you can see the mating SS surface, stainless steel surface is showing the continuous movement or shining marks, or you can say polished marks because of the continuous movement over this material. And let me tell you very frankly, uh, this was the most stringent requirement of performance laid down for maglev trains at that point of time, and the material was tested for it. It took about 6 months of continuous testing time to achieve these parameters, and the material was still intact. That means this material can still deliver more. But just because it was not desired, it was not required and not viable also commercially to continue that test further. So we can say that we still do not know the limit of this or capacity of this material yet. So when we have a side-by-side comparison of Ptfe with this UHMWP, wherein the sliding path is 5 times, the stress concentration or load bearing ability is double, and the velocity, high velocity movement which it can support is about 7 times. It is not a genius task to conclude that this material is suitable for fast movements. It can take very high loads and stresses, offers low value of friction, and thus offers the highest lifetime. So now coming back to the point from where we started discussing about the sliding material, because when you are looking for a improvement or innovation in a bearing system, you always try to eliminate the weakest component or weakest element, sliding material being one of that. And when we replace the Ptfe material with UHMWP, we are able to achieve a much longer sliding surface performance, and we are able to easily achieve a higher longevity and durability of the product. About the acceptance of this material, it has been widely used worldwide. It is developed mainly in Europe by a German company, so the European specifications are already accepting it, and it is also being accepted by other countries as well. In India, we have the IRC 83 Part 3, which is for pot Ptfe bearings. The latest revision in 2018, and the IRC 83 Part 4, which is for spherical bearings, which was published in 2014, and the amendments came very recently. Both these codes allows the use of UHMWP also inside the bridge bearing. So that way we have in our country also very well acceptance of the UHMWP sliding material. The next concern for a bridge bearing is the corrosion, because now we have eliminated one loose point, that is the sliding material limitation. We have a better material now, but corrosion becomes a major concern, no matter because of the environment around the bearing, or sometimes the bridges are in coastal areas where the salinity in the environment is very high. So all in all, this all leads to the degradation of the steel and it starts rusting and corroding over the period of time. So the same applies to the bridge bearings. It is no different. It is also made up of steel. So corrosion has been another enemy of bridge bearings. So there has been innovation in this direction also. Now there are certain improved aluminum alloys which have been developed, which can replace the traditional and conventional steel components of the bearings, and these aluminum alloys are so made that they do not require any corrosion protection treatment on top of them. What you see in this image is a sliding alloy which is finished with a special process, and this looks like a silver shining surface, a mirror like finish. And trust my words, this component is not given any treatment for corrosion protection. And if you put this material in the hardest of the environment or under the creek and saline water, and you take it out after 15 years and you wipe it with a piece of cloth, you will find exactly the same finish over there. So the innovation of this aluminum alloy and the use of this alloy in the bridge bearing, it not only now eliminates the corrosion concerns, it is also a very good load bearing element, so it doesn't compromise onto the load bearing capacity of the bearing, and also it offers very low value of friction when it slides against Ptfe or UHMWP. So this innovation of sliding alloy, it helps bearing to achieve a lowest value of friction, so the performance of sliding is further improved and the concerns of corrosion are totally eliminated. Let me also tell you over here at this point of time that aluminum alloys are not the only choice which are being used in bearings. In certain parts of the world, certain countries, they are also going for complete stainless steel bearings. If you remember, I told you a few slides before that there is a thin sheet of stainless steel attached to the main steel component to slide against the sliding material. Thin sheet because the stainless steel is comparatively to structural steel very costly, 5 to 6 times costly. But in many countries, to avoid the total issues of corrosion, they are going for a complete stainless steel bearings. In our countries also, there have been very few, maybe you can count on your fingers, very few projects where for some special requirements, they have gone for complete stainless steel bearings. So these are the possible innovations or advancements you can say to overcome the corrosion concern. There could be application in India also. We are often constructing submersible bridges also. By saying submersible bridges, that means there is a potential possibility that under heavy floods, the bearings can have a very high level of water, and the water level may sometimes touch also the bearing location. And you can imagine when the flood comes, it has everything inside mixed with the water, and that water could be the highest accelerating agent for corrosion. And if we have such applications, we can definitely consider the use of stainless steel bearings or the bearings made of aluminum alloy. Next challenge for bridge designers to handle in bridge bearings is the uplift. If we talk about standard single span structures, there maybe the requirement of uplift is generally not there. But when we talk about the structures which are continuous or maybe the structures which have curved inside, so for such structures, under certain condition of loading, the bearings which are installed on the outer part or at the extreme abutment locations may experience, in addition to the gravity loads, sometimes the tension loads also. So what happens when such tension loads comes into a bridge and the bearing system is not properly designed for it? I have been fortunate to have the actual reference of a project. This is the video taken from a pod bearing installed under a bridge where due to the repetitive tension loading, if you see very clearly, when the tension load comes, there is a clapping between the components or the anchoring system, and over the period of time, due to this continuous tension compression loads, the system or mechanism tends to go loose. And when this thing happens repeatedly again and again over the period of time, it raises fatigue issues, and at some point of time, the bearing system gives up. It gives up like this because the steel has always a fatigue issue, and when you are having a repetitive impact loading cycle onto the structure or onto the steel component, after a certain period of time, it may give you a fatigue failure. And when such thing happens, you could imagine the catastrophe that it could create. This portion of the deck was supposed to be held down by the bearing system. And when the tension mechanism of the bearing system failed, you could see very clearly in this image that deck with respect to the other segment of the deck lifted up by about 1 or 1.5 feet. So this could be the failure that if the tension mechanism or uplift mechanism of a bearing fails, it can create this sort of problems. So what are the innovations to handle this issue in bridge bearings? Now there are bearing systems which are developed and tested also and now certified also, which can handle any situation of uplift while satisfying the compressive or gravity load situation. This is a typical example of an anti-uplift spherical bearing. And the bearing system itself is so designed and so detailed that no matter whether the load is in compression, it is a downward gravity load, or it is a tension load, all the components of these bearings are in complete intact. There is no clearance or no play getting created, which could otherwise lead to an impact loading or fatigue concerns. Here it is also important to understand one simple but very what should I say, decisive fact, that the uplift is to be first understood whether it is a simple seismic uplift or it is a service uplift. If the bridge has a seismic uplift requirement, that means the uplift is only expected to come when there is a situation of an earthquake. And the earthquake may come maybe in once in a 10 years, 20 years or 50 years lifespan, or it may even never come in the entire life of the bridge. So for a seismic uplift, the design is not that challenging, and we as bearing designers can get away with providing some simple lateral clamps. But when it becomes a service uplift means it is a day-to-day affair. And by saying day-to-day affair, that means it may be happening every now and then in the bridge due to live load, or maybe due to wind, or due to any other reason. And it may be happening 10 times in a day or maybe 1,000 times in a year. Then the design of the bearing and the approach of the design changes upside down. And we have to take into consideration the fatigue design aspects, and the overall design philosophy of the bearing changes, and the bearing system somehow looks like this. So that was a brief about what are the challenges, main challenges in front of a bridge bearing, and what are the improvements and advancements that have been done so far to overcome those limitations and challenges and to improve the service life and durability of the bearings. Now, as I said in the beginning of the presentation, that we are no longer calling bearings as bridge bearings because they are now finding their ways, applications in bridge structures and bearings, building structures equally. So this is application, and this application we call as the isolation bearings. And the purpose what they do, if we understand this through this animation, if a building structure is integral to its foundation, and when the earthquake comes and the earthquake shakes the ground table vigorously, and because of the high lever arm and the anchoring of the structure with the ground, the structure also shakes vigorously and suffers permanent damages. And on the other side, if we have the isolation system inbuilt in the design, then what happens? The earth is shaking randomly, but the structure is doing a controlled movement. And this way the time period of the earthquake is shifted, and the structure is saved from having permanent damages. So here also the system which is used at this isolation locations are the bearings only, but they are little different types of bearings. What are these bearings? We understand. Let us also have a better understanding of this concept of isolation through this shake table test. In this, what we have two levels of the table. One is the bottom level, which is integral, and the top level, which is on the isolation bearings. And by the shaking of the liquid inside the glasses, the bottom liquid is shaking very high, whereas the top glass is more or less stable and the liquid inside is stable. You could imagine this is what the structure experience when the earthquake comes. So with these isolation bearings, we are able to control the movement of the structure, and this controls the damage that can happen in the structure as well. The isolation bearings again could be in different forms. They can be rubber based also, like elastomeric isolators. This particular is a rubber based isolator, and depending on the requirement of the structure, we need to have very high damping or low damping. We can have the compound selected accordingly, and then we can call it a low damping elastomer compound or high damping elastomer compound, and they satisfy different equations and conditions of the earthquake and the ground acceleration. This is the video from a prototype test of a high damping elastomeric bearing, and this is how virtually the bearing will be deflecting and moving or swaying left and right under the earthquake. Although this is a very slow test, but when the earthquake comes, there will be very high velocity, vigorous movement of the bearing. When the damping requirement is further increased and it is not possible by the virtue of the elastomer alone to fulfill the required damping, then the elastomeric isolators can also be combined with a lead core. And this lead core at the center of the bearing, what it does, it provides additional damping by plastic deformation. Lead, the pure lead, it basically is like a tough dough. We have dough, like in Hindi we call it atta. So it is basically something which has certain plasticity. It deforms, but it consumes a lot of force input while doing the deformation. But it doesn't reach to the ductile or failure limit. It doesn't break apart, but it keeps on deforming and consuming the force input. So that is what damping we call. So damping is basically consuming the force and dissipating it by some way, like by in terms of heat or some other way, and that's how the earthquake forces are dissipated. So this way the hysteretic loop is prepared, and this loop is nothing but it is the force versus deformation loop, and whatever the area that is encapsulated inside this loop is the damping that the bearing is able to deliver. Normally, in a application of isolators or dampers, the parameter of damping is ranging somewhere between 10% to 30% or 40% also, and depending on the required damping, the required choice of material is done. This is a simple equation to decide upon the geometry of the bearing, but as you can see, the time period in case of a elastomeric isolator, it depends upon the mass, that is the load onto the isolator, and the stiffness parameter, which is the property of the rubber. So we can say that in case of a rubber based isolator, the behavior of a isolator is depending upon the mass. This is the typical application of a rubber isolator in a bridge. It is done at the location of abutment, you can say more or less. And this being a cable stay bridge, again, the bridges like cable stay and suspension bridges are quite dynamic structures. They are considered and they have the highest amount of movement and dynamic rotation. And therefore, they might have the requirement of isolations also. The next in the category are the mechanical isolators, and we call them sliding isolation pendulum bearings, in short SIP. These are nothing but an extension, or you can say evolution of spherical bearings. They offer elongation of time period, The rotation capacity of these bearings is very high. There is no separation at the sliding interface in these bearings. They have no significant wearing because the majority of the components are steel with this high capacity sliding interface in between. And the recentering capacity of these bearings is not depending on the aging performance or load on top of the bearing. The working principle of these isolators can be beautifully understood by this animation. So I think this animation says it all. This is how the name of this bearing system is derived. There is a pendulum concept, and the curvature is so defined that by the virtue of this curvature and the total displacement we are allowing there, this bearing offers not only the isolation, but due to the friction at the sliding interface, it is also doing the energy dissipation. And then the recentering is automatically achieved because when it is going at the periphery or towards the corners, it is going up and there is a dead load on top of these bearings of the structure. So when the earthquake is gone, by virtue of the dead load itself, gravity loads, it comes at the center. So the recentering is automatically achieved. Let us also have a look at the high velocity test of a ship bearing in a test institute, and this is the explosive bearing being tested. And you could see at what fast magnitude the displacement can happen under an earthquake. And this way the bearing takes the movement and it offers the isolation. Okay, so we understood this principle of the design of isolation bearing. And now if we compare this formula of a mechanical ship bearing as compared to a rubber based isolator, there the function was depending on the mass and the stiffness of the material. Here the function is depending on the radius of curvature. So irrespective of what is the load on top of these bearings, by defining the radius of curvature of the sliding interface, we can govern the time shift or time period of these bearings. So how does it translate? It may be little difficult for you to understand what difference it makes, but this animation is now going to explain you beautifully how it matters. Let's say because of the geometry or the material behavior, the elastomer can be designed to work most optimally under a certain magnitude of mass. If that magnitude of mass is changing, the behavior of the elastomeric isolator is changing, which may not be suiting to the structure requirements. But a mechanical isolator is such, the behavior is entirely depending on the curvature profile and it is totally independent of the magnitude of mass. So this is an example of the LNG storage tanks, or you can also imagine some power plants or power projects which are located in high seismic zones. And if in this, for example, the LNG storage tank, when the tank is full with the liquid, it has a different mass altogether. And when it is empty, it has a totally different mass. And in such situations, the behavior of the elastomeric isolators change and they start doing erratic behavior. But the mechanical isolators in all situations, they have a very set behavior because the behavior is totally relying onto the curvature, which can be very precisely designed and manufactured also by machining techniques. So that was a brief about the innovations, or we can say the further developments and applications about these bridge bearings or structural bearings. We will briefly touch upon the aspects related to their performance. And firstly, I would like to discuss over here the installation aspect, because Many a times we discuss in too detail about the design and geometry and aspects like that. But it is to be understood that if a right product is not installed properly or it is not executed properly till the end, then probably the purpose or the benefit of that product is completely lost and it is not able to deliver the performance for which it is intended. So in terms of the installation aspects, we have to make sure you as a designer, you may be designing the bridges or you may be doing the execution part, maybe now or in future when you will be coming to the profession. It is important for a bridge bearing to ensure that the provision or location of the bearing is such it has the least chances of dust and dirt accumulation around, and the rainwater shall not be reaching to the bearing locations and spoiling the bearing because otherwise it will have corrosion. There shall be adequate provision of jacking points in the structure because no matter how good you design the bearings, there are always contingencies and there may be a situation, unforeseen situation where you need to take the bearing out for some repair work or some replacement. So the jacking provision should be there in the structure and the bearing shall be so installed that they shall be removable and completely replaceable. From site handling aspects, the transport brackets or locks which are provided in the bearings shall not be relied for lifting. We will see this in further slide in detail. Bearings shall be installed truly horizontal. This is an important aspect to take care about. And again, we will discuss in little detail in the coming slide. And the interface of the bearing at top and bottom has to be properly grouted. Otherwise, there is no point of installing the bearing over there. It will not perform. In case of movable bearings, the orientation is important. I will also discuss this in detail. In case of precast construction, this is an important aspect, but it is to be ensured that the girders are not getting launched onto the bearings with an impact. The girders shall also not be rested freely onto the bearings because bearings are the device which by virtue of their own design itself are offering resistance-free rotation. So if we leave the girder sitting onto the bearing without any side support, that is more or less creating a situation of an inverted pendulum. Or in very general terms, if I explain, it means then you are trying to stand on a ball. And it is very difficult that you are able to maintain a balance when you are standing on a ball, either you have to topple right side or left side. So the same could happen with a girder also if it is not rested when it is launched onto the bearing. So discussing the important and vital points in a little bit detail, transport brackets are not to be relied for the lifting. Whenever you will see a bearing, you will see certain components in the bearings which are marked with a distinguished color. And these are the transportation locks which are just meant to keep the entire bearing intact only for the duration of transportation and installation. When the bearings are installed and the structure skeleton is complete, these locks are to be removed such that the bearing is then free to move. But these locks are not having that much strength that when you are lifting the bearings or you are launching the girder, they can take all that load. So if they break apart in between the process of installation, then you are already having a dismantled bearing. So it is to be ensured that you are not lifting the bearings relying on these locks. Then selecting a right bearing for installing at the right location is very important. As we have seen in few slides, there are three configuration of bearings: fixed, a free which can move in both directions, and a guided one which can move only in one direction. And in the layout plan of the bearing in a bridge, there will be locations, pre-decided locations that where you have to place fixed, where you have to place free, and where you have to place a guided one. If by mistake you interchange these locations or you place the bearings wrongly, then rather fulfilling the needs and demands of the structure, the bearings can make a arrest in the structure, which could be very devastating for a bridge, and the bridge may even collapse because of this mistake. So it is very important. Orientation is very important. Orientation, let us try to understand by this bearing. This is a guided bearing and it is free to move in this direction and it is restricted for moving in lateral direction. Imagine this bearing is installed in a bridge by turning 90 degrees. So that means in the direction where the bridge wants to move, the bearing restricts that movement, and in the direction where the bridge should be stable, it should not be having any freedom of movement, the bearing allows the bridge to move, and this could lead to the entire deck sliding out of position and collapsing. So the orientation is also that way very important. Presetting is another important point. If you have presetting in your bearings, you have to make sure that the direction of preset is rightly placed. Sometimes in some special designs, some special cases, there may be a requirement of a rotation preset also. If a steel deck is erected and it is often given with an initial camber, or you can say longitudinal super elevation, which is expected to be settling down when the entire construction on top of the deck is over. That means the superimposed dead load and everything is over. Then this preset super elevation or camber is settling down. So for such situations, it may be required that the bearing is also offered with an initial rotation preset, such that when the construction is complete, then both the deck and the bearings are at the ideal location. So such important things are also to be taken due care in design and the application of the bearings at site. The bearings shall be installed truly horizontal. Now this is a very important vital aspect. If you study the codes for bridge bearings, even our IRC 83 part 3 for pod bearings, it very clearly states that the maximum rotation capacity of a pod bearing is 0.03 radians, and that too the rotation capacity for live load rotation, that means frequent rotations, is very low. It is 0.005 radians, and therefore it is very much important that you install the bearing completely horizontal. If you don't install it horizontal and these parameters are already missed, then the bearing is going to suffer a premature failure or problem. Why? Because let us understand through this animation, when the bearing rotates, this is the example of a pod bearing, the elastomer gets compressed and the other side it moves up. And with this compression of the elastomer, the sliding element also moves up and down. So when there is a frequent rotation and higher movement of the sliding material or the sealing rings, it wears over the period of time and it starts oozing out of the elastomer. This also happens when the elastomer is tilted to a greater extent beyond its limit to cover the gap and the effectiveness of the sealing rings is lost, then also the elastomer can ooze out, and therefore it is very much important that the bearings are installed horizontal. This is what we discussed in theory, and these are the photographs of the bearings from our own Indian structures, where due to some or the other reason, the elastomer pad has oozed out and come out of the bearing. Let me just show you some photographs of a bridge which we inspected. And here you see, after the inspection, the close inspection of the bearing reveals something is protruding from the collar of piston and pot, and this is nothing but the elastomer pad. And due to the ineffectiveness of the sealing element or maybe the construction tolerances, the elastomer pad has oozed out. It has come out of the bearing. And if such thing happens, this is the complete piece of the elastomer pad that has come out. The bearing is virtually non-functional. These are some other failure photographs of the bearings from inside. If the effectiveness of the sealing element is not there, then the elastomer can suffer permanent damages, and so the steel components as well. Another issue which is a very important point in performance of the bearings is the restoring effect. The restoring effect of the elastomer pad. If you refer to the IRC 83, you will find this equation there inside. and this equation is for the restoring moment or the elastomer stiffness. And what it caused a detrimental effect on the sliding material. And why? We understand through this animation. As I have been saying all throughout my presentation, that the elastomer has a restoring moment or a rebound effect. Uh, in very general terms, if I try to explain you, if we put a rubber band in between our fingers, and if we try to pull it apart, we feel certain pressure on our fingers. And when we relax it to its original position, the pressure is gone. That means elastomer applies a counter force to regain its unstressed position. So similarly, when the elastomer is compressed inside a bridge bearing for rotation, it applies a counter force, and the sliding material on top, which should be getting a uniform load, it gets concentrated on some part, and there could be a separation on the other end also. So when this thing happens repeatedly over the period of time, the sliding material, which is just a thermoplastic material, it destabilizes and it flows out of its position like this. This is the sliding material flowing out of its position. So these are all the issues or troubles associated with either the poor installation or poor manufacturing of the bearings, or in some cases we can say the wrong selection of the bearings for a particular application. So these are very important aspects in that way to consider. Here I have again taken a case study to explain you. This is the Sigma Bridge in Hong Kong, which at some point of time or maybe today also is the longest suspension bridge in Asia, and it is again a rail cum road bridge. And the bearings which were installed in this bridge, I think this bridge was opened to traffic around 1993-94. They were Ptfe spherical bearings, but you could say within 4 to 5 years of its operations, the Ptfe has given up. The bearing has failed like this. And then these bearings, the design was improved and the sliding material was changed from Ptfe to UHMWP. And the first batch of replacement of bearings in this bridge took place around the year 2000. And since then, it's already more than 20 years, and the replaced bearings are performing satisfactory. So that was another aspect. Now coming on to the eccentric loading. Uh, First of all, let us understand how the eccentric loading or bending of the sliding plates can happen. First of all, if the load transfer from the superstructure onto the bearing is not uniform, it is concentrated towards the outer face of the bearing, then the sliding plate can buckle or bend. This can also happen when you are using the in situ concreting. That means you are just putting the shuttering around the bearing and the bearing is installed in place and you are pouring the lean concrete. The lean concrete as such has no stability of itself. It is free to flow, and under the influence of this lean concrete weight also the plate can bend. And there are certain designs of these structures, like in case of railways, there are open web girders where there is no stiff bottom component there, and there are two webs which are on the outer periphery of the girder, and therefore the load transfer onto the bearing is again eccentric. So for all these reasons, the bending or buckling of the top slide plate can happen, and if the thickness of the plate is not adequate, then that could lead to a lot of cascading and devastating effects. The sliding material, one of the most common failure in such bearings is when the sliding material is uniformly loaded, it has certain thickness which is for the purpose of providing the translation, but when the plate buckles, the sliding material at the periphery is squeezed out, and also there is a steel to steel contact which renders the bearing totally non-functional. So this is another installation aspect which we must ensure and we must say that it should be fulfilled. Last but not the least in the installation is the grouting of the dowels. We have to ensure that the bearing is adequately supported on firm and sound surface, whether it is concrete or it is steel, both on top and bottom. Why this is important? Because again, through a case study, one of our project where we were informed by the client that within 2-3 years of the installation, the bearings has failed. So we were concerned also, and we were amazed also that how could a bearing can fail within 2-3 years. And we went to the job site and we started doing the investigation. So let's say this is the situation of the bearing looking from the outside. This is the pedestal grout material. And then we started digging out the grout material. We started chipping it out. We removing the grout material. And when we reached to the inside portion, we have removed the grout up to here. And when we reached to the inside, there you could see. I don't know whether it is visible clearly in the image or not. The grout material is only at the periphery and at the inside central area where actually the load transfer is taking place, there is no grout. It is hollow. So imagine if the bearing is not supported by a firm concrete surface from underneath, how it could bear and transmit the loads. And as a result of this, the entire bearing component bent in the hollow portion. This is the shape of the component which bent. Not only it deformed, but it also developed crack. And not only the crack was there in the bearing, but it was also there in the pedestal. And the component also cracked, and even the elastomer also had the crack at the same location. So this could be a problem if the bearing is not supported firmly and not grouted properly from bottom and top. So that was a brief about the installation aspects. Now maybe quickly in another 5 to 10 minutes, I will touch up the quality control aspects because they are very important for you. You may be tomorrow going for the acceptance and inspection of the bearings. So it is very important for you to understand what are the aspects of quality control. We can divide them in 3 main groups. First, you can say is the test on raw material. Then we have in-process inspection, that is during the production process, what shall be inspected. And the last but not the least, in fact, the most important is the finished product testing criteria. So the raw material test includes the properties assertion, whether the chemical and mechanical properties of all the components, steel, rubber, Ptfe, UHMWP, whether they are all okay or not. It is as per the code, and the property and the strength of the material is fulfilling what is taken in the design of the bearing. That has to be ensured. For that, you do the chemical composition testing as well as mechanical properties, tensile, yield strength test. The dimensions of the castings is also very important to ensure that the machining, after machining, you get the desired dimension. The soundness of the casting is also important to ensure that you can do by NDT testing like ultrasonic test. But sometimes when you are at site and you are not having all these equipments at your disposal, then some handy checks like hammer test. You tap the surface of a steel with something in your hand, another steel rod or something, and it should give you a uniform ringing sound. If there is internal hollowness inside the component, then all of a sudden the sound at that zone changes. And also you can do a weight. The weight of any component where if it is having internal defects or hollowness will be reduced because there is no steel, it is hollow inside. So by such quick check, you can ascertain whether the component is sound and it is good for use or not. Similar applies to the elastomeric components. All the important tests like polymer identification, raw elastomer content, etc. should be done. Other components also to be checked for their properties, for their fitment inside the assembly. Once the raw materials are checked and they are taken into the production process, then there are a series of tests applicable during the production process. I am going through these because it is all clearly mentioned in the code. We need not to go through it in detail at this point of time, but it is an important aspect, so we have to just cover it. One of the important in-process inspection is the ultrasonic inspection, which gives you a fair idea about the internal soundness and integrity of the component, the steel components especially. Then the weldings are to be checked for their integrity by die penetration test. The finish of the stainless steel also to be checked because we discussed this already. When this stainless steel sheet will be sliding against this material, it has to deliver the lowest value of friction for two reasons. First, the lower value of friction it is giving, it is offering less resistance in the structure and no stresses is getting created in the structure. And the lowest friction also ensures that this material wear and tear is minimum and it will be giving you a longer service life. So these are all the in-process checks that are to be done on a bearing. And last but not the least, the most important one is the finished bearing test. When the bearing is finished, the code says that it has to be checked or the parameters of performance, the vertical load, horizontal force, whether it is able to offer the desired rotation and what is the value of friction. All these parameters have to be verified by testing, full scale testing. And for this, the test presses are used. Such reaction frames are used where the bearings are placed inside and it is applied with the design load or maybe 110% or 120% of the design load. And after the testing, the bearing should not show any sign of damage or distress. So that was a brief about the manufacturing and quality control aspects. Last in 2-3 slides, I will be just taking you through some of the project references which we should be proud of. It may be a surprise to you to know that the largest bearing ever used in the world, size-wise, is used in our own country. And this is a project where it has been used. It is a signature bridge in Delhi. And this is a cable stay bridge. And there are two big bearings at the base of this pylon, which is holding the entire main span. And each bearing in this location is designed for 17,000 tons service load and 23,000 tons ultimate load. And you may not be able to appreciate what 17,000 tons of load is all about. A fully loaded multi-axle truck also that you see around, that may be weighing around 30, 40, 50 tons, not more than that. So you could imagine maybe how many hundreds or maybe even thousands of trucks, if you place together, then that will make this much amount of load. And that is the load for which these bearings are designed. And these are the bearings, actual bearings. They themselves are the size of about 2 meter or 3 meter. And every bearing itself was weighing around 20 to 30 tons of weight. They are not, in fact, one of the largest, they are the largest bearings to the best of my knowledge ever used in the world. Then few years back, 2-3 years back only, Mr. Modi inaugurated the Bogeyville Bridge in Assam. It is a strategic bridge connecting towards the most eastern part of our country. It is near to Guwahati. And this bridge also, it was having a conventional arrangement of some pot bearings with some seismic restrainers like this. But then they also eventually decided to go for a spherical bearing arrangement with a standard 4 bearing configuration. This one is a fixed. The bearing in front of fixed is a long tunnel guided. The bearing next to a fixed is also a guided, but it is the transverse guided. And the fourth one is a free bearing. Then the Atal Setu bridge in Goa, Mandvi bridge also we call it. It is also one of the monumental structures in our country which has been constructed and opened to traffic few years back only. This bridge also is having very high challenges in terms of designing and movement requirements because it is a continuous cable stay structure, you can say. Not only one span of cable stay, but many spans of cable stays are there. And it's a very heighted structure. So this bridge also have been designed on special bearings and they are based on spherical with VHMWP. So the references are several, but the whole purpose of combining all these pictures together is to have an understanding that Bearings involves a great amount of engineering and technological insight. They looks to be very simple products, but they are very complicated products when it comes to design and detailing. Expansion joints often get some attention because they are at the road level. And if they are not good or they are not properly installed, they easily comes to notice. Anyone who is crossing the bridge is commenting on it and they get attention. But the bearings, once they are installed at such a location which is not easily accessible. So if you are not installing them properly, then probably the next time that you are able to have the attention on the bearings is when they have developed a big problem. So it is therefore very important that you design a bearing right, you manufacture a bearing right, and you install them also rightly. And someone has said, and very beautifully they have said, that we can get the best output of technology only when it's combined with the best of quality and workmanship. That's what I was trying to explain. And the joints, when they have problems, they make noise, but the bearings, they suffer quietly.
Some kind of fundamental knowledge that I want to give to the listeners. And I start with the word truss bridges, usually or lightly called. And then I call this open web girders because the second phrase really impresses me because basically they are girders, and of course the webs are open. So the open web girders, you will learn from a short while from now that it is appropriate to call a truss bridge as a open web girder bridge. Okay. Let me go to the fundamental of how the load carrying happens in a bridge or in a truss member. Then we move on to study how the force flow that happens in a truss structure, because trusses are basic workhorses. They are the primary gravity loaded systems, and then we are also going to learn how they have been integrated to deliver what is required of transferring the live loads and superimposed dead load. Right. The first thing that I given a very simple one. I have a member, a prismatic member, which is longitudinally loaded. Right. But then the load is applied in such a way that the axis of the member getting shortened. So I call this as compression. Right. Now, if we go to the next one, same load parallel to the longitudinal axis of a prismatic member, but then it is applied in a direction in which the centroidal axis get extended, right? So we call this as a tension. Mind you, I am using the words extension and compression, uh, which are the loads being applied, parallel to the longitudinal axis. Okay. If I make an arrangement of members, right, there are some systems, right, some systems which take the load purely by tension and compression. So we say a load is carried by a combination of tension and compression. So the blue being compression and the pink being tension. Okay, fine. So of course, there also I used to say the triangle is the most basic unit in any truss system. This system is geometrically unchangeable, and then it is determinate. Okay. So if I can make, the formations of the truss during this, using these basic units, I can develop any number of structures, any number of different types of trusses that I can prove. Although we use normal shape of trusses, it is possible with the basic unit you can put together an innovative truss, absolutely no problem. But then you need to follow a little bit of rules to, in development of the truss forms. Okay, fine. I'll go to the next problem. I'm just slightly varying. It's again a prismatic beam, but it is loaded perpendicular to the axis of the member. Correct. In the earlier, the load is carried by tension or compression. Now, what happens if I apply a load perpendicular to the axis of the member? The load is carried by moment and shear. When I teach structural analysis, I find some of the students draw the bending moment diagram in page 1 and then shear force diagram on page 2. Okay, both complement each other, both are twins, and they never be separate. Even in a design, what we have seen is people give more importance to the moment design, and shear design is only a check. Correct. So I have already told in the last lecture, it is because of the shear rigidity the moment comes in structural systems. Right. Now, this is the bending moment diagram. Right now, one of the things that if I want me to comment on the bending moment diagram and shear force, I'll say the bending moment diagram has, I wouldn't say one sign, but the entire curvature is in the, cup-shaped bending. Correct. Of course, the bending momentum should be down on the tension side. That's fine. Leave it then. Now, if we take the shear force gets split right into, let's say, a positive or negative. Usually, like last time I told you, it is better to draw the shear force diagram like this. Right, this one is like this, and this one is like this. Very simple. And then I mark the bending like this. Right. So the 2 points I say is the bending moment has the same type of bending, but in different quantities varying over the span, and the shear force changes. One more point I want to tell you is in this example, there is a coincident maximum of bending moment and shear, right? The cross section at the center is subjected to a coincident maximum of the bending moment and shear. Okay. Now I go to a distributed load. Okay. So again, my load is perpendicular to the longitudinal axis. So 100% it has to take the resistance comes to the combination of moment and shear. Okay. Now in this shear force diagram, if you see that the moment is maximum here, somewhere here the moment is maximum. Let me see if I can change the color. Yeah. So you can see the shear is maximum over here. So unlike the last time, there is no coincident shear and bending moment. The cross sections at the center are designed for the maximum bending moment, and you need to see the end cross section also take the shear. So in design situation, there are two things that will come. Okay, now enough of bending moment. So I would say this is a girder, right? The very reason I said I will always like the word girder to say a truss, primarily because I'm talking about bending moment and shear. So why do I want to call this? What is this? This is a member. I would say an arrangement of prismatic linear members. I don't call it as a truss. I may give a different name, but I would say this is this is a support. This is a support, and usually it is better to call this as a formation, right? It's a formation. So, what is a structure? A structure is nothing but a combination of formations and supports. That's how a structure is made. Now, what is the big question about this formation? So these are reticulate formation and very popularly called as trusses. Correct. Now, what is a truss? That is loaded perpendicular to its longitudinal. You can see the load that is applied here. Correct. Now, what is a truss? Okay, just now I have introduced two types of structural behavior: loads which are parallel to the longitudinal axis, and members which are perpendicular, loaded perpendicular. So in the case where the perpendicular load applied to the perpendicular to the axis, the the load is carried by moment and shear. Right. So I design my truss as truss is nothing but a beam or a girder that carries bending moment and shear. Why? Why? It is because I go minimize it. Right. It is because primarily it is bending moment resisted by a combination of tension and compression. Most of the students I talk or young engineers I talk, I say, sir, it is only tension and compression. Where is the bending moment? What is this bending? Bending moment is only comes in beams. Correct. Now, of course, any system, be it a solid one or a reticulated one, when the load is applied perpendicular to its longitudinal axis, it will take bending moment and shear. So all truss structures are open web girders, quote and unquote, so that they take bending moment and shear, of course, by a combination of tension and compression. Let us see how that happens. I also have some examples to show you. This is the most popular example. I always love to explain that we have a rule in the design of plate girders that the moment is carried by the flanges and the shear is carried by the web. Correct. Why do we say that? Right. Now I have the area of the flange, which is really maximum, and I have, let's say, this Fy, right, the maximum. So the larger area into larger stress gives me a significant amount of compression force in the flange. Now, if I take a little part of the web, what I do is the area is very less, basically because the thickness of the flanges will normally higher than that of the web. So if I take, and the corresponding stress is also lower. So what we say is, even you please go and calculate for a parallel flange beams, you more than 90% of the moment is contributed by the tension compression system of the flanges. So what we say is moment is carried by the flanges. Right. Now coming to the shear diagram, right, what we see is the flange part of it, the component of the flange part is absolutely very less. And then using the shear, right, the web stake. So what we say is, if I can make an average part of the shear, then I'll say the shear is taken by the web. Correct? Sir, mind you, I'm going to make an analogy between this simple behavior into the trusses. Correct? Now, here we say moment is carried by the flanges and shear by the webs. Right. Now, what happens now here in a truss? Same thing. The truss has to take the bending moment and shear. Right. So I have a chord member, which is called a top chord member, and this is a bottom chord member, and I will call the vertical incline members as web members, right? Very similar to my a plate girder. So my chords are like the flanges, and my incline and vertical are like the web. So what I'm saying is very interesting observation. The moment is carried by the chords. The moment is carried by the chords. and shear by the vertical inclined members, or simply it is easy for me to call them as web members. Correct. Now, this is the analogy between an I beam, which is the most efficient, cross section for bending, and similarly, the trusses are a very good configuration for taking moments and shears. Right. Now, how do you get the moment? Very simple. We know the top will be under compression, and it is given an opposite force in the bottom. They are basically separated by a distance. So when I have two forces separated by a distance, I will get a moment. So that's why I say, taking the analogy, I say the chords take the bending moment. Right. Coming to the web members will take the shear. So whatever the loading comes, the shear variation is resisted by the web members. And also I would again tell the one part which I've observed is that because of the shear rigidity, the bending rigidity appears in any member. Even if you take a solid eye prismatic beam, because of the shear rigidity, bending moments happen. I will show it to you in a minute. Okay. So now we are going to the next part of it. Why I'm saying is, why I'm bringing in the analogy between a beam and in the truss, which are reticulated, is that all the concept that we apply to beam systems is also applicable to truss system. Basically, they are girders and they are flexural members. Right. Now, first I will take a thin beam. What is a thin beam? I think I've lost. Um, I'm sorry. So a thin beam, this is L and this is D. Of course, I am marked for this L and D. Right. Now you can see is a beam is very thin if my L by D is very large. The large in the sense, 15 to 20. Right. If in that case, I say the flexure the flexure dominates the action, because as I told you from the first figure, whenever there is a load perpendicular to the longitudinal axis, the load is carried both by moment and shear, complementing each other. Right. Now if you can see, why I'm saying is, if I draw a deflected part, now what happens? Cross section, my cross section will, it's perpendicular to the axis. Now you can see here, the cross section rotates, and I say the flexure dominates. And now what happens to the shear? If I take the shear deflection happens like this. Right. The shear deflection happens like this. Of course, this is the center line. So what happens? The deflected shape is almost straight, and the cross section just slide between each other. So we call that behavior as shear dominant behavior. Now, for the L by D is very less, something like 4 or 8. 4 and less are very unlikely in the case of trusses. So if we have these kind of systems, then we say here in this one, the flexure predominates, and here in these trusses, the shear predominates. Now, what is the difference? I have purposefully shown a thick line for the cards, right? For the cards, and thick line for the web members. So what I'm saying is, if it is a flexural dominated truss member, then you will find the cards take large force for the force transmission. Right. Now, the web members are not I mean, they're not relatively, not loaded as the chord members, because in a flexure dominant member, the chord, I mean, the moment is carried by the chords primarily. Now, coming back to the shear dominant trusses, you will find the web members, the vertical or the inclines, which are called the web members, they will be more in size compared to the chord members, because of the low L by D, the shear dominance is there in that. So why I'm saying is, I would always want the students or engineers first to check what is the L by D, right? Whenever you're given a system, right? For example, the other day we were solving, the span was 60 meters. The next question is, what is the height? Okay, it's 10 meters. So 60 by 10, 6. Now the question comes, is it a flexure dominant truss or is it a shear dominant truss? So, or in the borderline. Why I'm saying is, this gives you a beautiful idea about your preliminary design. What are the sizes that you can choose, right? Straight away, you can choose higher members if it is a flexure dominant and for the chords and for the web members, right? So I would request everyone, every young student and engineer, first of all, question what is the length and what is the depth, and have an aspect of what is the L by D ratio, and you start get a feel of the numbers, correct? How you're going to design, and you can also see how the members, come in place. Right, sir. Now, I'm going to go to take a topic which, um, some of the students will feel bitter, correct? I know some of the students, I told you, you go pick up your strength of materials book. They say, oh no, right? Now I say, I'm going to take you to the one which is actually beautiful exposition of things. Is it your influence line diagram? Because why I'm saying is influence line diagram. At least for some simple truss, the students must sketch and try to, understand the force flow. And you say how the influence diagram gives me a very good comprehension of the force flow in the system. Okay, right. Now we have a 6-panel truss, and I have 4 meters, and every panel is also 4 meters. And this is an N-type truss, which I will come a little while from now. What is the different formation that we can have, things like that, right? I am actually looking at the top chord member. You can see the top chord member is blinking. So normally what we do is, in a simple rule, if it is a chord member, we will find an opposite node, right? We find an opposite node. That means the member from this joint, I mean the member two joints joining at a point is an opposite corner. Now, what is the force in the member U1, U2? It is nothing but you have to write a companion beam. Because why? Because truss is nothing but a flexural system, correct? So what I do is, in the companion beam at the node I want, I write the bending moment, correct? Now, what is a moment? What is a moment? I can get the the coefficient, but then the number is not important. So what is a moment? A moment is nothing but two equal and opposite forces separated by a distance. So very simple is that I have the moment value here. I have the moment value M, right? And I divided by the height, let us say height, right? Then I should get the force in the member. Very simple. So just by drawing the companion beam bending moment diagrams, I can easily find the member forces. It also gives me a feel. Correct. I'm going to ask you, what is the pattern that you are seeing? So an upper chord member, right? It is nothing but on the opposite joint, opposite node, if I draw the bending moment diagram and divided by the lever arm, which is basically the height at that point, which is 4 meters, and this is the 1 by 4, you will find, and that's the member. Correct. Now, we are saying that the force in the member is something to do with the bending moment. Okay, I'll go to the next one, in which I'm bothered about the lower card L1, L2, L3. Okay. Now, in that particular case, again, I have to find the opposite node, draw the companion bending moment diagram, a companion beam, and for that, I will draw the bending moment diagram. Okay, for the cards, why I'm taking the cards? Already we have seen that in a system, the cards take the bending moment, right? Now, what is the, the value for the bottom card, which is plus over here? This 1/4 is divided by H. Again, it is M divided by H is equal to my force. Very simple. So I get the card force, right, simply by drawing the bending moment diagram. Now you can see here, right? So whenever the load moves on the entire span, if all the 6 panels, the sign of the chord forces do not change. So I also want to show the earlier one, that the sign, because on the entire span the load moves, the sign of the force does not change. Correct. Now I move on to a vertical member. You can see the vertical member, right? I want for U3, L3. So for the vertical members, we don't locate an opposite node, we locate an opposite panel, right? We locate an opposite panel. Then I draw this, I draw the companion beam. And for that, I would, draw the variation of, the force in that. Now, what happens is that my vertical force member, right, changes sign. Let's say I'll say plus or minus, because why does the change takes place, which is not in the chord members, is because if I take a moment, the moment does not, the sign does not change, at least in the simply supported system. But then the shear force changes sign. So we see the vertical and the web members, since they take shear, they will vary as the shear force variation in the beam. I'll go to the next one, which is an incline panel. In the incline panel also, we will use an included panel, and we draw the companion bending moment, the beam, and then I draw the variation with that. Right. Of course, we know that the loads are applied between the nodes, so there will be a variation between the nodes. Now we can see here the value of the inclined member changes to plus and minus, basically because variation of the shear force. Okay, so this is the basic learning is that, right? Now, one more thing to prove, which I will show you in a minute, in that, see, this is my bending moment diagram. This is my bending moment diagram. So I'll try to change the color. Right. So this is my bending moment diagram. And then my corresponding truss form is like this. So this truss form follows the bending moment diagram. So what will happen? So we are nearly come to what is called a funicular truss. What is a funicular truss? Predominantly the axial force flows in the arch direction. I will show you a very simple example from right now. Now you have a double overhang. So you're going to have, some of the moments which are going to change from positive to negative. So I can have a configuration system which is with respect to the change of the bending moment. Now, why I'm saying is, whenever you see a truss, a bridge truss, which has a form, we can easily relate that these stress forms are related to the type of bending moment that they occur. So that's the point I'm trying to show. I will show with a simple example of how the bending moments really dictate the force flow in a truss member. Okay. Now, um, before going to the topology, let me go back. Um, discard the annotations. Okay, I will minimize, or right. So I'm going to run some. Are you able to see my screen, sir? Are you able to see my screen?
Yes, sir. Yes, sir.
Yes, yes, it was
Okay. Right, right. So now I have okay this. So this is same a truss which is edge loaded, right, which is a cantilever truss, correct. So I'm going to show you that. Let me analyze this truss, and it analyzes. Done. I go to the post-processing mode. I select this, apply, okay. Right, now I'll come back to the deflected shape, little bit in a larger this thing. So this is the deflected shape. Now imagine the load was at the tip of the truss. This is a cantilever truss, correct. Now, forget it. I go for the force transfer, correct. Force transfer. What I want you to, the young engineers and students to understand is how the chord forces vary, how the chord phases vary. Because the bending moment diagram is 0 on the edge and it is going to the maximum at the supported end. Now you can see the chords. So from the edge to the support, the chord forces keep increasing because the bending moment keep increasing in that. Now look at the web forces. They are constant. The inclined members and the vertical member forces are constant throughout the truss. What does it say? That they follow the shear force variation. So in a simple cantilever truss, right? So the chords take the bending moment and the shear is taken by the web. Beautiful. That's really fascinating to know how the trusses offer the load resistance to that, right? So this is a very beautiful example to say that, the vertical members are constant and the inclined members are constant because my shear force is constant throughout. Now the chord forces vary because the bending moment is 0 and at maximum at the fixed end. Okay, good and a nice example. So let me close this and I go to it's another one. It is another one. So basically it's normal truss, normal prod truss. Let me see the load. Okay, a central concentrated load, simple central concentrated load. So I go analysis, right, and done. And let me go to the post-processing. Okay, load case, apply, okay. So let me, the deflected shape is too much there. So this is a deflected shape. I'm not too much worried about that. But then I go to the members force distribution. Member force distribution. I get the same. You can see the variation of the chord forces, both in compression and tension. You will find the variation of the chord forces, right, follows a triangular variation of the bending moment. However, right, the shear force is constant, right. However, on the left hand side, I may call sometimes, let's say, a positive shear. On the right hand side, I have negative shear. Now, all the inclined members are under tension. Why? Because I have reversed, right? This is called an N-type truss. I put the diagonal left to right, and then on the next half, I have turned into right to left. Now, if I had continued left to right, left to right, left to right, left to right, you will find all the other three members will be under compression, right? Now, this is the load because the web members vary as the shear force, they will change sign. So, because of the advantage that we have in this kind of trusses having uh, the moment is taken by the flange, we take this advantage. Okay. Now go to the other one to prove. Okay, this is a very common truss. Okay, let me see what is the load. I don't know. Okay, good. So this is a central concentrated load. Okay. Now, can some of the engineers, right? I'm not going to come and check some of the engineers, young people and participants. You have a pencil and paper. Can you just guess the kind of forces in that in this truss? It's a triangular. This is a fink kind of truss. The name is fink. Right. Now, can you guess what will be the force flow? I've been teaching you that, any bending moment is shared by a combination of compression and tension. Now, the bending moment variation dictates the member in the forces. Any young engineer can guess, because I'm going to give the results in a short while. Please check your answer. If somebody is not solving it, God bless you, my dear. God bless you. Okay, try and see. You can see here anyway. This is my displacement diagram. I'm not really bothered about that. What I want to show you is a beautiful one. What's happening, sir? What is happening? This has become a funicular truss, correct? It's completely, the two members, directly the load goes to the support, correct? A funicular. Why is that? Because if I have a companion beam with a central concentrated load, if I have a companion beam, it will have a triangular bending moment diagram. Now, if I make my truss structure parallel, in the shape of the bending moment diagram, it is a funicular one. So, right, you will get the entire load is dispersed through a compression on the cards, right? One more look at this. You can see here, right, the formation is made in terms of the bending moment diagram. Okay, excellent. One more last example I will show you. It'll be quite interesting for you to see. Okay, so this is it's called a Spandrel Arch. Okay, so the curved one is an arch, but these vertical members are called spandrels because when a load goes on top, these spandrels will transfer the load to the trusses. Simple one. Okay, the load diagram, let me see. Yes, the simplest one, but there is a load top and at the bottom. Correct. Now I analyze it. So can you now guess? Anybody can guess what will be the kind of behavior? Anyway, I will make the displacement shape. Close that. I'm going to open the force flow. It will be very excellent to show, right? It is very excellent to show that the spandrels merely transfer the load. Of course, sir, this is not for common loading. I'm using a unitary load to demonstrate the flow that happens in trusses. See, these kind of spandrel arch trusses are very common. Now you can see this gives you a beautiful idea about how the tension and compressions are varying. You can see here the variation of compression is like our warrant truss. But if you take a warrant truss, the web members will change in compression tension. So what we are seeing is a warrant truss action combined with an arch action that happens in a spandrel arch truss beam in the girdle. Okay, fine, sir. So I'm very happy that I was at least able to demonstrate to you that not only the bending moments are shared by bending moments are shared by chords and the shear force and by, web members, but I also showed you how the force flows really happens in a truss system. Of course, these two are examples. Now you will relate it much more easily that the truss shape and they become almost a funicular truss. Okay, sir. Now, the second part of it, I'm going to teach the truss topology. Okay. So, do you ever look at the topology of a truss? You have, you have traveled through hundreds of trusses when you go on a train. Because you see the other truss. Have you ever thought, like, what is the topology? What is the shape? Because all are rectangular trusses with, war and prot and verticals and several other things. But then you should be able to understand the topology of simple trusses, right? What do you mean by topology? I can teach it for a long 2, 3, it'll be an amazing subject. We can say how we can integrate several trusses and we can make our own truss on that, right? The topology means, the way they are arranged and there is some mathematics behind it. But I would like to emphasize that there is no mathematics without the physics of it. That's the point I want you to teach in the topology. Okay, I have the basic unit. I already told you. I'm going to make a formation. It doesn't have a support, so it is not at a structure. So what I do is I add one node and two members. No, I'm just counting the members and the joints. I'm only adding one. So I'm going to add one joint and two members. And I'm going to join another joint and two members. Right. Now, what happens? I am governed by the relation. If I go, the number of members equal to 2j minus 3. What is that minus 3? Right. It can also be written like this. The indeterminacy is member plus number reactions minus 2j. Right. Both ways I can always solve a system. What is the big thing about it? What is the big thing about it? Whenever I see, I'm sorry, whenever I see a topology of a truss, if it is whether determinate or indeterminate, or it is geometrically changeable, right? It is nothing but sometimes, in our classic books, it's called stability, but I want to use the word geometric changeability. Okay, fine. I'll go to the next one. Okay, look at the first one. Let me go to my, yeah, you can please look at this one, right? Please look at the one, right? Does this follow my rule m is equal to 2j minus 3? Of course, yes. 1, 2, 3, 4, 5, 6, 7, 8, 16 minus 3, 13. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Beautiful. It satisfies us. How about this? How about this? Right. Same one, the number of members are the same. Now, it obeys that, but that's what I said. The mathematics, it doesn't exist without physics. Now, many students will find out. So this one, right? This one is unstable and that will make the truss geometrically changeable. Now, why am I adding? Now, imagine I'm adding one more member. Right, one more member, right? So I'm sorry. Where is my pen gone? Oh, I need to this highlighter. Oh, not pen. Okay. So what happens if I add another member here? Right. Now what I do is this formation has more members than my equation m is equal to 2j minus 3. So what is that m which satisfies 2j minus 3? Is the number of members which is just enough to keep the formation from to make it as a geometrically unchangeable system. Correct. What is that? If I add more members, that means I have more members that are added to the system that is needed for the geometric unchangeability of the truss. Correct. So we call these as redundant truss, and we count the number of members more than what is required for a simple geometric unchangeability as indeterminate truss. Right. What is the use of indeterminate truss? You will find just now I showed you, that without this truss, right? I go back again and use my eraser. Right. Now, what happens if one member has failed? Right? If one member has failed, for example, if this is failed, there is no failure on that. Right. Now, because if this member has failed, there is another member to take care of that. So we call this force flow redundancy. That means failure of one member do not cause the failure of the system. That is why in some cases, we will make the trusses statically indeterminate, or we add redundancy to make sure that any one of failure of one or two members do not cause the system failure. Now imagine the first one, right? Imagine this member fails. If this member fails, then this will go into a mechanism. Correct. So it becomes geometrically changeable. So what happened in a determinate truss system in any bridges, failure of one member is failure of the entire system. But in the case of an indeterminate truss systems, the failure of one or two members, of course, you have to ask how, and based on that, there is a path of redundancy. So what I want to teach the young people is that usually the numbers of members added more to the system is primarily to give the force flow path. Okay, let me watch my time. So I started 5:30. Okay, I'm at 6:30. Fine. We will cover. I mean, don't worry. Those are watching the clock or ready to go to the restaurant for a weekend dinner. Wait, I will finish it fast. Okay, sir. So now my question is, what about the third one? Please look at the third one. Right? What is the topological? What can you tell about the topology? Is it a determinate truss? Right? It is a determinate truss. Or what is that? That is, you are saying in the topology. Correct. So you count your members. I'm not going to count it. I'm not very good in arithmetic. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So I said 2 into 19, 38. Right. 2 into minus 38. Minus 3 is 35. I should have 35 members in this. It appears to be a stable determinate truss. So let me count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. Oh my God. So I have to get 35, but I have 33 members. Now I want to ask you is this topology geometrically changeable? Why is the entire truss system doesn't work? Number one, it is not a formation. Correct? The first reason I am saying is it is not a formation. It is a structure. Now, why it is a statically determinate structure is that I can take this as a beam system in which there is a suspended span at the middle. This is suspended span, and you can see an overhang which is stable. This overhang is stable, and This is also stable. So this is a stable truss system. In fact, you will see the Rabindra Setu, the so-called Howrah Bridge, has a very similar concept of this. The advantages of this is called the father-child concept. When the load when the load is in this span, the others won't get, but in the middle, the other two get. If the load goes to that, right? So that is for you to say. So what I'm saying is there are several cases in which you have to understand the topology to interpret whether the system is geometrically changeable or not. Correct. So this is what I want to try. Any try systems, don't accept it, please. Right? Don't accept it. Look at the topology. Understand what is the L by D, which is going to be shear dominant, flexure dominant. That is what is needed in this. Right. Now, I'm going to take you to a journey of how a truss system work. There are three types of trusses: through type, deck type, and semi-through, which I will come to you. Right. Now, I just now we saw, okay, just now we saw, um, where is my pen? Just a moment, sir. Right. Sir, I would say, okay, there is a load, the deck load, the floor load. I am applying here. I'm applying here. On the other side, I apply. Let us take this truss. Right. Let us take this truss. So what happens? Yes, this is a stress subjected to vertical loads. And where is my cursor? Oh, okay. So this is subjected to vertical loads. So this member will be under tension. Slowly I have to move. I lost member. Just a moment, please. Just a moment, please. The tiny the mouse cursor.
Your cursor is right now near the stringer word you have written.
Okay.
Got
Okay,
it?
right. Yeah,
Lights go
yeah,
down,
I got
lights
it.
down. Yes, got it. Yeah.
Okay, okay. Yeah, thank you. Your eyes are extremely good, ma'am. Okay, so
Wearing specs.
okay, so this is in compression done, right? Then I can simply say half the deck load, right? Half the deck load comes on each truss. So I take the half the load. Now look at the my bottom this. So the load flow is whatever load that comes on the deck. Let us say any medium that gets the load, right? Transfer it to the longitudinal members. These longitudinal members aggregate the force. They go into the cross members, which will go into the truss, and they carry the load. And you will see at the bottom, there are some incline members are also provided between these two truss. Correct. Now let us see why are they for them. Right. So I want to introduce two concepts in this design. One is structural design. One is structural design, right? So the other is integration design, right? The other is integration design, right? The other is integration. What do you mean by integration, sir? Of course, in a plate girder, I will. Yeah, in a plate girder, right? In a plate girder, right? Sorry. So I have vertical stiffeners are provided. They don't come into my calculation. They don't come into momentum calculation. So what we do is in a truss bridge, there is something called structural design, because your basic workhorses are the truss systems, And then you add several other members called the integration design. Because why is the integration design? Because it will make the other two trusses to work performly, work correctly. And just like just like a stiffener in a plate girder, that will enhances the behavior. Let us see what is the integrative design, because we have studied the structural design to this thing. Okay, coming to the top one. This is the truss one, this is the other truss two. These trusses are connected by an incline member. Wow. Say on the top, I have another truss, which is the horizontal direction. Why should I have a truss? Because I will have a vertical truss if the load is vertical, right? Why should I have the truss in the horizontal direction? It is because you have some wind loads coming on this here, right? Let us say your wind loads coming on this. Now, these loads are in the plane of the truss. What about the vertical load? The vertical load is also in the plane of the truss, and similarly the horizontal load. So what happens is primarily the top girder is introduced as a wind girder. Or what happens if the horizontal forces, right, actually flows through the trusses to the from one truss to the other, and we can, in the wind load, we can calculate shielding. Without shielding, that's a different thing. Now my question is, the vertical stresses, the trusses, the structural trusses, right, the structural trusses, this one and this one, right, they have a support. They have a support. The load flow to the support. If I take the force flow, the load comes onto the deck, right? Comes onto the deck, goes to the longitudinal beam, goes to the cross girder, goes to the truss, goes to the bearings and bearings, go to the pier and goes to the foundation. This is the load flow. Now, what I'm saying, asking is, what is the load flow for the horizontal truss? For this horizontal truss, right, where should the load go? The load finally has to go to the support, because the entire has to be there. Now, how the load will be, this says, the load will be transferred as a portal action. As a portal action, right? I cannot put an X brace, no, nothing can go, correct? So this portal is called an end portal, in which it will aggregate the horizontal truss force and it will transfer it to the foundation, to the bearings, right? So this is the integrative design. We really don't know about, about what are the things needed. So we need appropriately, right? Now you can see here, the see here, the end portal is given with a brace, knee brace, right? Which is actually, trying to give the rigidity to the corner members, because this acts like a portal, and using the portal action, it is transferring, right? Now you have some kind of right, you have some girders over here. Why? Because these trucks take the load, the other trucks take the load. What is this doing? For example, in the train or in a track, we have something called racking loads, which will act, I'm sorry, my line, say, which is act in this direction. It's going to shake in the transverse direction. So I do not want my truss forms to change the shape. So we introduce we got sometimes called sway bracings, right? So we introduce this member. So what I'm primarily trying to say is, in the total structural design, we have structural design and integration design. So the members or the braces that I provide and how I integrate, it depends on the force flow of the structure, is called the integration design. So A bridge design truss is not complete without the structural as well as the integration design. Anyway, I'll go quickly. This is again are different types of trusses, correct? So please question their validity. What is the difference between this and this? Pratt and Howe truss, right? I don't know. You have to find out. What about a Warren truss? In a Warren truss, can I remove this vertical? Can I remove these verticals? Right? What are the verticals are doing? Sometimes they are zero force member, right? If I have one load unload, this member is a zero force member if it doesn't have a load. So please question the validity of each configuration. Don't take it them for granted. So look at the validity of them, correct? So there are different sizes like Baltimore, subdivided Warren, Caterers. Please question the validity of providing this member. It is not like Rangoli, correct? So it is not like I started at 5:30, 6:30. Okay, I'm 1 hour 15 minutes. Am I right?
Yeah, you
Yes.
have completed 1 hour 15 minutes.
Okay, okay. So many of them are, like me, they started looking at the watch because the dinner is getting cold in the restaurant. Anyway, I'll finish it fast, my ladies and gentlemen. Please question the validity of additional members. This is what I call as, topology. Why at all a K-truss? What is the big this thing about a K-truss? Correct? Please learn. I'm going to share the PowerPoint. Please look at it, and then if you want to do analyze how the truss bridges, sir. Otherwise, I'm telling you the simple go to a Stat Pro, apply the load, find the force, design the member. That's not the way I want you to think. Right now, it is all our learning is to the classical learning. Suppose if the the load moves, we go to the pointer. See, if the load moves on the the top chord, we call it as a underslung, sometimes a deck type truss, right? So there will be a difference in force flow between the the through and the deck type. Underslung is this, and this is semi-through. That means the truss bottom and the rail bottom, the rail top may not be there. Here it is on the bottom. So there will be a small difference between these two. So we call as a semi-through truss. The other one is the through truss. In the through truss, on the bottom chord and whichever formation of longitudinals we make, they work. So there are three types of bridge trusses. Of course, this I've already taught you, right? You can see the top are in compression, the bottoms are in tension. Now, this is a Warren truss. We call it Warren because you can see the W in it. Oh, nice. Now you can see in a Warren truss, the tension compression alternate on one side, right? You can really find why. So in the case of a prod truss, right, the one which is shown below, you will find, for example, in this particular case, you will find in this case, you will find all the diagonals are one particular force, right? Okay. Now these are for usage of 30 to 150 meters, correct? Similarly, the other two. So this prod truss is 30 to 100 meters. You know why the maximum span is reduced? You will find that the vertical members that are provided, right? If it is long and you're going to have the dominance in the chord members and you have more number of web members which doesn't contribute to the economy of that, right? This is the famous truss that you have would have seen, and I want you to really see what is that. It is shown here, which we have just studied a few moments back. Okay, now this is a highway girder, right? This is a highway girder. You will not find much of the truss bridges in the highways, correct? It is basically because, in the case of a train bridge, so the spacing of the trusses are very close. So when there is a load, a better load transfer takes place in the trusses, right? But suppose you have a deck of 15 meters and you have a truss in between, and probably the efficiency of the truss is not realized. Anjanelu sir, did I say it correct? Anjanelu sir. Oh, is he there or
He's
is not?
not available now. Yeah, he's not
Okay,
available.
okay. Harsh is there?
Yeah, absolutely
Yes,
right.
yes,
Absolutely.
he's
Go
there.
ahead. Perfectly right.
Yeah, because we have a wider deck, the contribution of the truss action is not there. So I haven't seen much of highway these things, but then railways, it is their major workhorse in that, right? So this is a composite deck supported on a truss bridge, right? See, there are other bridges which are movable. You can see here, this is called the track girder. I will show you in a minute. And you can see here, there can be a horizontal movement that we can have if we want some navigational way or something like that, which I'll show you in a short while from now, right? We also call the Bailey bridges, right? These bridges are, quick time bridges. I remember in our Commonwealth Games, just before days before that, some structures failed and the spectators asked to move into the stadium. So they quickly made the Bailey bridges. So they are fast bridges mostly used in the Northeast to cross maybe deep gorges and things like that, right? Now, usually the span ranges in highways is about 30 to 120, railways about 120 to 50. You can have long trusses even up to 550 using the concept that we just see, balanced cantilever. Like that, you can have a larger thing, right? Which are the materials which are competing with the trusses for the smaller spans plate girders? Because the trusses are not really useful. Right, and the intermediate span box girders and very long span cable stayed bridges, you will find them to be much more economical. And the span to depth ratios, my dear friend, in the very first time I told you, you have to look at the span to depth ratios. You will see for railways, it's 10. For the highways, it's 15. So I can say the railway bridge is a dual. There will be a good dominance of moment and shear. But then in highways, I see more a possibility of the shear getting dominant and your chord forces will be more. Anyway, there are different configuration. What you must do is the diagonal should have a minimum slope and you should make the members in such a way that there are no rigid joints because we are analyzing the structure as a pin system. So in the detailing of the system, what I do is it is better to, if I have three members, there are one member, I'm sorry, um, there are three members joining, I will make sure that the CG of this member, right, and CG of this member coincides. The reason is very simple, correct? If you do the equilibrium equation, we say when three reactions are concurrent, the system is unstable. Why? It cannot resist a moment. So the concept we used here is the reverse way. If I make all the CG lines of the system on a single point, you will find they are not able to resist moment. So it's a hinge joint. So avoid eccentricity so that we get secondary stresses. However, I want to give you a little clue. Whether you are using a hinge or a frame analysis, not very different, gentlemen. The secondary effects are not very deep. So you can analyze using a pin jointed assumption and then make sure that the connection rigidities for the secondary moments are taken care, or you can do a frame system and you can take for actual moments, you can take it in the connection system. But in my opinion, there's no big difference for truss systems, whether you use a pin jointed or a plain frame. Not very much difference on that, right? And coming to the design, correct. Now, If it is a compression member, we use, right, as short as possible. Correct? Now, if it's a Warren configuration, be careful in the tension member, they will alternate between tension to compression. Right? In the prot, we give shorter compression member by introducing the vertical in between. So for the compression member, my length is a problem. Now, when you do the topology of the truss configuration for bridges, you must see how the members are added so as to reduce the compression effective length, right? Usually because the compression is governed by the Euler buckling stress or governed by buckling beyond a point. So primarily, we always worried about this thing. These are the typical sections that we use for compression members, right? In the case of tension members, I'm not worried about the L by R because I'm not worried about the slenderness because basically in the tension, but then my worry is on the net area because we have seen according to IS 800, your tensile strength is minimum of gross into yield plus net into ultimate and block shear. Either these are three. So what I'll do is I'll try to provide a section. For example, these are the cross sections which are available both for compression and tension, but I have to make in connection in such a way that I will get more area in the design of tension members, right? In the case of diagonals, absolutely the first word has come. The diagonals, tension bar compression. Why is that? Right. In the influence line, we saw that since the shear force changes sign, your inclined and vertical members can change sign. So that is why the vertical and diagonals are, either you have to check whether the member is fully under tension or fully under compression, or it changes when the shear force changes as the load move across it, right? So the sections are very similar. Sometimes I can unify for medicine, right? Now this is our integration design, right? Look at the bottom now here. The top cord is under compression, right? The top cord is under compression. Let me go change the color, right? The top cord is under compression and this is also under compression because I'm seeing, look at the truss one. This is the truss one and this is the truss two. I'm looking from the top, right? Now what happens? I have put a brace like this. So this brace hasn't any way reduce the length of the member. But then if I go for a diamond brace, correct? So this is compression, this is compression, this is T1, this is T2. Now the effective length is reduced to half on the compression side. However, here you have one joint all together. Here you should have one joint here, another joint here, another joint here. So there is always a economy that kicks in, right? How much you are going to save in reducing the effective length member vis-a-vis the amount of connections that you need to provide to get the reduction in that. So it is always an interplay. There is no a straight answer to that. Okay. So in the case of integrative design, you need to put the members in such a way where the effective lengths on the compressions can be reduced by introducing something like a secondary brace, a delta brace, and like that. So you are free, your game, you can pitch and play with the provision of the braces. Anyway, this is the normal one. This is a normal truss we can see, right? You can see here, what is this vertical member? Why it is provided? Right, it is provided to divide the compression cord. So then why here? Right, why here? I have given you one example. Please analyze and see why it is that. Right. So this is the truss. Now in the through cross section, as I told you, at the ends I have end portals which are heavy size because the load from the top cord, I mean the top horizontal bit, should flow to the foundation. So they are there. They are also intermediate and they will give you the forces, racking forces, which will shake the bridge in the transverse direction. Now look at the top. Just now we saw how we can integrate the top. This is a diamond brace that we have provided. Now look at the integration design at the bottom, right? We have something called braking force and right? So I have a burst like this. So, right, if the if the driver applies a brake, so there is a force, longitudinal force that is transferred, correct? And if we reverse it, is in the other direction. Now, similarly, when the trains run on the lower cards, they also the braking and uh, the 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 tracking and the braking effort are there, which are basically longitudinal forces that occurs at the rail top, correct? So they have to be aggregated and they have to be transferred to edge. So what we provide is what is called braking girder. We introduce, this is again an integration design where the longitudinal forces are aggregated and they are supported on one side of the bridge, correct? Finally, the forces should flow to the end. That's what we see. To a cross girder, finally it goes to the bearings. So this is the the structural design, and this is the integrative design at the top. This is the integrative design at the bottom. So I've given you a good idea about the truss bridges. Now, in the analysis, I should take the rigid joint effect. I used a plane frame, and if there are non-nodal forces, I need to, because in all the truss we say the nodes are loaded. We can, of course, introduce in today's computer software, apply the loads in between. We need to take the temperature, eccentricity. This we have already seen. Connections are very important, and this is the welded connection. You can see here there is a small transition given. This is to avoid stress concentrations in in stress concentrations. What happens if you have let's say I'll show you a simple, let's say a tension member for you to show. Like, let us say I have a weld here, right? One weld. Now, if I draw the stress diagram for the member, right? Ideal member. This is my stress diagram for the member, right? Now, for the so for this joint, it goes here at the joint, it shoots up. It is because of the the discontinuous in the weld, the defects in the weld. This will actually enhances the stresses at that point. So in order to avoid that, we give a smooth joint in order to avoid, because fatigue is all about what is the difference between the stress. Fatigue is nothing but cyclic application of stress. So what we are really worried is the delta sigma, the variation of stress. Imagine at this location, the stress will be varying like this. The stress will be varying like this. So I will get a larger delta sigma, which will cause my fatigue light to be lower. So in the case of welded truss, we need to take care of the detailing properly, correct? So this is the normal bolted and riveted joint, which we have seen. And we can see this is the, you can see the end portal, my dear friend. I was just talking about that end portal. Wow, it's a very strong member, because it will have to transfer the load from the top to the bottom. Okay, so this is the normal. You can see here, right? This is a simple taper truss. It follows the simple bending moment. Simple. You will find the top chord for members are, high. All other web members are very thin, because it follows the shape of the bending moment, because in a simply supported span. What about here? The truss system is a continuous span. Now you can really see the the bending moment variation, if you draw here, if you have a support, if you have a support here, now your bending moment will go like this, will go like this, and go like this, right? So wherever there is a continuous bending moment, we also accordingly make our, this is what I want. So all young people, whenever you go, you should look out and see what is the bridge topology, right? Here, one interesting is that it is a deck type up to this, then it is a through type up to this. Correct. So it is a combination of a deck and through. And of course, this is, I showed you the most famous bridge, and is, please go to the thing and study the philosophy. This is our, I think someone has to mute the mic, please. Someone has to mute the mic. Sir, someone has to mute the mic, please.
Farkis sir, could you please mute your mic?
Okay,
Yeah.
sir.
Yeah, so these are the the Bailey bridge. Anyway, these are typical connections. I'm near to the end. Yes. Now this is a navigational lift bridge. Navigational lift bridge. Correct. What I do is I have two towers. In the towers, there are the truss bridge is lifted for the navigational way. After the navigational the passage, it will be pulled down to space and it will become a through bridge, right? So in Rameshwaram, right, the existing Shirzar span has been abandoned, and I think it will be the traffic will be closed, and a new bridge is being built, and in that we are using the same concept of the lift bridge. So maybe another 1 or 2 years, the Shirzar span will be replaced by a lift bridge. These are movable bridges in that, right? So this is the Rameshwaram Shirzar span. And you know what is the beauty of the Shirzar span? Right. Suppose if I have one wing here, if I have another wing here, they will rotate like this, right? When you open it, it will rotate like this, right? These two arms. Now, what Shirzar did was, Shirzar did a beautiful thing. For the same span, now what happens, because there are counterweights here, these are counterweights here. If you tilt the balance, the truss will automatically go and will open like this. The truss will automatically go and it will open like this. So you get more navigational way. So this is, slide and rotate, or they said, there's a particular word I forgot, right? Roll and lift, I'm sorry. It is a roll and lift. So it rolls away and then lifts it up. So you get more navigational way. Only for this, Shirzar was given a patent, and Shirzar got a patent at the age of 32, 33, but he died, and that benefit was received by his brother, and this was done from England, and it is transported and it has crossed 107 years, still up and running, and then some repairs are to be maintained. Anyway, the last one is about bridge launching example, right? I want to give one example of a launch truss. Usually when the trusses are launched, we attach a member called a nose, launching nose, correct? So this launching nose is attached to cover the horizontal space, right? So what we do is we'll keep moving the nose with the truss, and of course there is a if needed, we put a counterweight, and it is moved to the place, right? And this is the one which was pulled by these two girders, done by my friend Chokalingam in Trichy. So the trusses is moved in place slowly. Now you can see the trusses is moved in the place. There is only one, so there is no need of the launching node. This will be dismantled and you will get the truss installed, right? So different types of launchings are there depending upon the topography, depending upon the congestion, whether it is a city or in a green field. So the mechanism is this, right? Usually, this I have stopped here. Do I have 5 more minutes, ma'am?
Yes, sir, you have.
Yes, sir.
Yes, sir,
You
you
can
have.
take, continue,
Yeah.
sir. It's still,
No, ma'am, because the dinner people are ready, so I don't want to disturb them.
no, it's still 5:30 over here in India.
No, ma'am, what is the saying that there's a weekend day? Anyway, sir, I want to
Yeah.
show you how ingenious the launching can be. Okay, so I was really wondered how a person from Trichy, here they did the launching of the a bridge in Sri Lanka. It is an arch bowstring bridge. This I'm showing to purely inspire. Okay, I have not seen in a textbook. All that I have seen cantilever erection, there are so many types of that. I have not seen for the first time. This is called a fishing erection. I mean, it was named, I don't know, Harsh has to say whether it has been done elsewhere in the world. And of course, this is the river. Let me, yeah, this is the river, and we have two piers with the on piles built, and this is the completed deck is completed up to that, and we have to launch this steel arch, a bowstring arch you can see here. So we need to now what happens, it is first moved up to the thing because you got three supports. There's no problem. It will be stable because it has got a positive support. Now, you can see a tower is erected here. A tower is erected here, and then what happens is that the the arch is slightly pushed inside, right, using a counterweight at the bottom. Now we are pushing the truss away, and then for the stability at that support, we need to have a counterweight. So this counterweight is actually made and it is pushed. At that time, we put a raker pile and we make an anchor point. This is make an anchor point. Still the counterweight is available. Now we are attaching a string. We are attaching a string at the top, and two ends of these girders are cut and they are slightly being pulled. Now, what happens when you pull? You can see here there is a black roller is there. Now, when you pull this, this moves on up to this. Is moved on up to this. Then what happened? It is slightly adjusted to tilt, so that we can take the roller off and put it in the other position. You can see the black roller being moved. Now, this is the a beautiful technology which I really saw. The truss was, went into a little bit of imbalance, and then after that it is lifted up, right? So once it is about the entire weight, the back of the weight is on the piers, and then these I will show you how they. You can see here. This is an intermediate stage. This is the full bowstring stretch. Bowstring arch bridge is being launched, and it is being held by two towers. You can see it is tied and it is pulled into position. And see here when it comes nearly, you keep shortening and put the thing in place. So this is what really amazing to me, how they are able to till the truss, I mean, still with the downward load coming and with all that, it was done by a professional called Chukkalingam. He's got practical knowledge. He's got tremendous practical knowledge. So I'm really admired how he gets these ideas for launching. And after that, it is launched, right? So using the fish pole technology, this is launched, and this is the actual truss which is existing in Sri Lanka. So you can see this is being launched on from one side. It's very difficult in a deep river.